Hello everyone, my name is Mpoki Mwaisela and I'm a PhD student at the University of Neuchâtel under the supervision of Professor Pascal Felber, and I'll be presenting the in-memory acceleration for homomorphic encryption with UPMEM PIM. So I'll go through quickly homomorphic encryption, then I think everybody's touched on PIM, talk on HE kernels, and talk on the evaluation. So what is homomorphic encryption? So generally, homomorphic encryption allows us to perform computation directly on the encrypted data. That way we have the highest level of confidentiality in the sense that we assure that our data is encrypted both in transit and while it's being processed by the cloud providers. And so the potential use cases for homomorphic encryption are enormous, includes privacy-preserving machine learning, secure data analysis and processing, and secure system and transaction. However, homomorphic encryption has a significant large overhead for this type of application, and we try to check if can UPMEM PIM help minimize the homomorphic encryption bottlenecks. So the first question is where the overhead comes from. So we compute direct on encrypted data. So what happened, and computing direct on encrypted data on ciphertexts, which are generally very large compared to the plaintext. If you look at it's at least 50 times increase on the data size compared to the plaintext, which leads to the general problem that we have, that the ciphertext is way larger than the plaintext, making this type of encryption very memory intensive. So homomorphic encryption takes its background from lattice cryptography, which has been proven by cryptographer to be resistant to quantum computing attacks, and utilizes the complicity of learning with error. And so generally the learning with error is that you have a plain text and you try to put a bunch of noise to the initial plain text. That way you can encrypt directly on the ciphertext. This way, with this noise, you have to make sure that the noise is manageable in the sense that you don't exceed and you can retrieve back your ciphertext. So we have a number of constructs and schemes that have been developed, which include the PGV, BFV, and CKK. So these are the schemes that are used and being explored on how we can leverage them on the application aforementioned. And the thing about these schemes, they all have the similar primitive, which you have things like generating the keys, the normal primitives that we have for most of the encryption algorithms, that is encryption and decryption. And the most importantly for homomorphic encryption is the evaluation phase, which include the eval add, for example, eval rotate, etc., like eval multiplication. So for the problem of ring learning with error, so by ring means that we are working on polynomial rings. The data representation are in polynomial formats, which are in a ring format in the sense that we work on a specific finite field. So in a specific polynomial form as this one. So from there, since we are working on a ring, a ring is an algebraic form, is an algebraic construct, which asks to have at least addition and multiplication to have a fully complete ring having with it. And then since you have addition and multiplication, the thing that you can have on polynomials, the type of operation includes addition, multiplication. Well, addition is straightforward. You can just do a modular addition operation like this. However, multiplication is a bit complex and requires us to use a specialized algorithm like Barrett's reduction or Montgomery reduction algorithm for efficient computation. So to sum up, we have a big bottleneck in homomorphic encryption due to the high bit width. The first thing is because we have very high degree polynomials in homomorphic encryption. And another problem is because we have coefficients in polynomials which have very high bit width. But this is managed by one of the algorithms that is called RNS, shortened for residual number system. So what it does generally is that it splits this very high bit width coefficients into multiple coefficients which can be executed individually. So there are quite a lot of literature that have been focusing on accelerating FHE schemes. So most of these literatures, as I mentioned, they focus on either optimizing the algorithm that we have, including the transforms, bootstrapping, and encoding. So with the transform, the idea is that I mentioned we do polynomial multiplication, coefficient-wise operation. However, to achieve this level of operation with the polynomials, we have to transform the polynomials from one form to another form. So we have to convert the polynomial from the entity form, which is coefficient-wise applicable to perform the operation on it and then take it back to its normal form when needed. Another very important algorithm is the bootstrapping algorithm. So the bootstrapping algorithm, like I mentioned, homomorphic encryption intends to all the homomorphic encryption, they intend to introduce some kind of noise to the initial plain text. In this way, you have a ciphertext. So the bootstrapping algorithm is an algorithm that is used to manage the amount of noise that you have, in a sense that later you can retrieve back your initial ciphertext, in a sense that you can decrypt, because as you continue on encrypting the data, it reaches a certain level, you cannot, you have so much noise in the sense that you cannot decrypt anymore. And then you have the encoding, just to have a ciphertext, and then encoding it into the polynomial format, and have these slots to. So hardware that have currently been used include the DPUs, FPGA, AVX, that are currently on the market. So processing in memory. Well, I think we've touched a lot on this. So we just have a bunch of DPUs with us, embedded with DRAM chips, and each DPU has access to 64 megabytes of RAM, exclusive access, and each chip has 8 DPUs with it, and they are generally general purpose processing. And programming the DPU, you have the host application and the DPU application, and the host includes orchestrating all the operation for the DPU. So ABUMPIMP PIM as an accelerator, basically we use the polynomial arithmetic algorithm as kernel for the DPUs. This is straightforward like that. That's what we use. And then we try to leverage the massive extensive parallelism that is provided by UPMEM PIM. So with the evaluation, we use the host and the PIM server with the 32 DPU rank, and it's 128 gigabytes of memory and 248 DPUs. And we measure the CPU execution time, DPU execution time, and host memory. So to start with the evaluation, we have a case study of OpenFHE. So OpenFHE is a library that have this implementation for homomorphic encryption, and it includes features from various other libraries, including Pelisad, HLib, which is from the Intel, and it supports a majority of efficient implementation for BGV and so over. So one important key feature about this library is that it includes the hardware abstraction acceleration layer, which we supports pointing multiple backends for acceleration. Our ciphertext, as I mentioned, they're in a polynomial format, but to be precise, they're in a format called DCRT. So DCRT is a combination between the entity and RNS. I will explain briefly. Entity is a transform, so it transforms a specific polynomial from one domain to another, from domain A to domain B, in a sense, so that it could be it could be viable to perform operation coefficient-wise. While RNS, it intends to split up the coefficient to fit in a specific machine bit width. So our evaluation, we have, so this is for this polynomial addition, and we have a polynomial size and the execution time here in seconds. So we run this with the one CPU thread and with no copy. You can see that we achieve a greater deal of speed up for this polynomial addition. So this indicates, this shows that we can perform homomorphic addition and speed up from one CPU thread. Same with when we do the copy from the host machine to the DPU, we can get an amount of speed up. However, if you compare it with the multi-thread application, so with multi-thread, what we do here, we just turn on and off the OpenFHE library, OpenMP flags. We don't do much, and we can see that we have speed up for higher number of data. But however, we lack when we are doing copy. So the main bottleneck is the copy operation. So it's the same for multiplication. So it's a Barrett's reduction and multiplication. Here I'm talking specifically about coefficient multiplication. We get speed up, which is similar to the addition, both for one thread and multiple thread. But however, with copy, we get a little bit of we don't get much speed up. So lastly, I will talk about the number theoretic transform. So like I said, we transform polynomial from the entity for efficient multiplication, and existing cooperation include the CT butterfly operation for entity and GS butterfly operation for INTT. And what's interesting here is the data access pattern for each butterfly operation. So B stands for butterfly operation, and the main issue we have is between operation we have data dependencies, and so we can see that our results for this type of for the transform that we have is that we need copies. We need to update the tables between iterations. Yeah, and yeah, it's not ideal for the UPMEM PIM in general. And yeah, so my conclusion is that homomorphic encryption, we perform computation on encrypted data, but it's very slow. Still, it's an open problem to find accelerators to accelerate homomorphic encryption to make it more usable in different scenarios and application. HE can benefit from UPMEM PIM massification. So here, to be more precisely, is that with the results that we have, with the two results we have for polynomial multiplication and polynomial addition, what we can do is to design a homomorphic encryption algorithm in such a way that you skip this transform. How you do that is that you have what we call leveled full homomorphic encryption. So you set your ciphertext to support a certain number of operations. So let's say 50,000 operations, and then you skip this type of operations. So the application becomes more compute intensive, and hopefully you manage to resolve the data copy issue. And yeah, you need to efficiently manage the data copy to host DPU. Yeah, and that's it.